On March 15th, 2026, satellites orbiting far above the Arctic Ocean recorded something that had never happened before in 48 years of continuous measurement. Sea ice in the north reached its winter peak at just over 14.2 million square kilometers, statistically tied with the previous year for the lowest maximum ever observed since satellite tracking began in 1979. Less than a month later, on the opposite side of the planet, something almost impossible to reconcile was unfolding. Antarctic sea ice, which had spent most of the preceding year sitting well below its historical average, suddenly stopped collapsing. Strong winds pushed it outward through the Weddell Sea in January and February. By the time it reached its yearly minimum, it had settled at a level close to the long-term average, nearly 700,000 square kilometers higher than the catastrophic record, low measured just 3 years earlier. 2 poles, 2 opposite stories, both unfolding in the same 12 months on the same warming planet, and neither one behaving the way the textbook said it should. This is not a story about a single dramatic headline. It is a story about 2 ends of the Earth pulling in different directions at exactly the moment when climate models expected them to be moving in sync. For decades, the assumption baked into public understanding of climate change was simple. The planet warms and ice melts everywhere, steadily, predictably. That assumption is not wrong exactly, but it is dangerously incomplete. What is actually happening at the top and bottom of the world right now is stranger, more chaotic, and in some ways more unsettling than a simple story of steady decline. To understand why, we need to walk through what actually happened this year at both poles, why scientists were caught off guard by parts of it, and what a growing body of new research is revealing about forces that have been hiding underneath the ice all along. Let's start in the north because the Arctic's story this year is, on the surface, the most straightforward. Every winter, as darkness descends over the Arctic Ocean and temperatures plunge, seawater freezes and the ice pack grows outward from the permanent ice cap at the pole. This expansion typically peaks in March, before the returning sun begins to melt it back through spring and summer. In March of 2026, that peak arrived at just over 14 million square kilometers, a number that sounds enormous until you realize it barely edged past the previous winter's total, missing it by less than 30,000 square kilometers, a difference so small that scientists classify the 2 years as statistically indistinguishable. In plain terms, the Arctic just recorded, for the second year running, the least amount of winter sea ice ever measured by satellites in nearly half a century of observation. Numbers like that can become numbing if you only hear them as abstractions, so it helps to picture what 14 million square kilometers actually represents, and then to picture what losing even a sliver of that means. The Arctic Ocean's ice cover is roughly the size of Russia at its winter peak. Shaving off a few 100,000 square kilometers might not sound catastrophic in isolation, but the real alarm bells for scientists this year were not about the maximum extent alone. They were about what lies underneath it, quite literally. Ice extent, the flat 2-dimensional footprint you see mapped by satellites, tells you how much area is covered by ice. It tells you almost nothing about how thick that ice is, or how much of it will survive the summer melt season. And on that front, 2026 delivered a genuinely unprecedented result. Total Arctic sea ice volume this past March was the lowest ever recorded, lower than the previous record set just 1 year before, and roughly 15% below where it stood in 2024. Modeled ice thickness data from Danish meteorological researchers showed that across most of the Arctic basin, the ice sitting at what should be its yearly thickest was less than 2 meters deep. The only regions holding on to genuinely thick, resilient, multi-year ice were a narrow band running along the northern coast of Greenland and through the Canadian Arctic archipelago, exactly the kind of last refuge pattern that ice scientists have been warning about for years, as the Arctic's once vast reservoir of durable multi-year ice keeps shrinking into an ever smaller corner of the map. One climate scientist described the state of the ice entering late winter this year as one of the weakest in the entire satellite record. Language that is notable because scientists in this field are usually careful, measured communicators who avoid dramatic phrasing. When researchers who spend their careers looking at charts and confidence intervals start reaching for words like alarming, it is worth paying attention. And the mechanism behind the alarm is straightforward once you understand it. A record low winter maximum, especially one built on unusually thin ice, does not just represent a bad year in isolation. It sets the starting conditions for everything that follows. Thinner ice melts faster and more completely once the sun returns in spring. A weak winter buildup gives the summer melt season a head start, which tends to produce an even lower summer minimum, which in turn means less multi-year ice survives to seed the following winter's freeze. It is a compounding cycle, and once you are inside it, each year makes the next year's recovery a little bit harder. There's a strange nuance buried in the 2026 Arctic data that deserves attention too, because it shows how misleading a single national headline number can be. While the overall Arctic ice pack was thin and weak nearly everywhere, one region did something almost the opposite. In the Bering Sea, the stretch of water separating Alaska from Russia's Far East, ice extent this spring was near the highest level seen since 2013. In parts of that sea, ice pushed further south along the Alaska Peninsula than it had in more than a decade, rivaling extents last seen in the early 2010s. Meanwhile, just a few hundred miles away, the Sea of Okhotsk, west of the Kamchatka Peninsula, recorded its lowest ice extent on record for that same time of year. And the Greenland Sea sat among the 5 lowest extents ever measured there. This is the part that should reshape how you think about polar change generally. The Arctic is not melting as one uniform block, growing weaker everywhere in lockstep. It is fracturing into wildly different regional stories, some seas essentially collapsing while a neighboring sea temporarily surges, all beneath one overall downward trend line. Local wind patterns, ocean currents, and short-term weather systems are increasingly capable of producing outcomes in one basin that look nothing like what is happening a few hundred kilometers away, even as the broad, multi-decade trajectory for the Arctic as a whole keeps pointing in exactly one direction, down. Now travel to the opposite end of the Earth, because the Antarctic story this year is where things get genuinely strange, and where the phrase, "scientists didn't expect this," earns its place in this script most directly. To understand why Antarctica's 2026 sea ice numbers caught researchers' attention, you first need to understand just how bizarre Antarctic sea ice behavior has been over the past 15 years, because the far south has spent over a decade violating the expectations built into most climate models. From the start of the satellite era in the late 1970s through roughly 2015, Antarctic sea ice did something that genuinely puzzled climate scientists and, in certain corners of public debate, was even used to cast doubt on climate change itself. While Arctic sea ice was declining steadily and sharply, exactly as greenhouse warming models predicted, Antarctic sea ice was doing the opposite. It was slowly growing, not by a small statistical wobble either. Antarctic sea ice extent reached record highs in 2012, 2013, and 2014, even as the planet's average temperature kept climbing. Researchers proposed a range of explanations at the time, from shifts in precipitation, freshening the ocean surface around the continent, to changes in wind patterns driven by the ozone hole, none of them fully satisfying, none of them able to completely explain the anomaly. For years, the Southern Ocean seemed to be the one corner of the planet's climate system that was simply refusing to follow the script. Then, starting around 2016, that pattern didn't just weaken, it inverted abruptly and dramatically. Antarctic sea ice began falling, and it kept falling, culminating in a stunning collapse in 2023 that wiped out an area of ice roughly equivalent to the entire landmass of Greenland, producing the lowest sea ice extent ever recorded around the continent. It was one of the most abrupt, unexpected shifts ever observed in a major component of the global climate system, a decade of anomalous growth followed by a hard, fast reversal that outpaced what most models had anticipated. Researchers have spent the past couple of years trying to explain what actually happened, and a study published in Science Advances in 2026 offers what is probably the most complete answer yet, describing what its authors call a compound, triple driver behind the destratification of the Southern Ocean. The process by which the layered structure of cold, fresh water sitting on top of warmer, saltier, deeper water broke down. For decades, that layered structure acted almost like a lid, a stable barrier of relatively fresh, cold surface water sitting above a much warmer, saltier layer of deep ocean water. As long as that lid held, the deep heat stayed locked away from the surface, and sea ice could keep forming and even expanding, protected from the warmth pooling just beneath it. But the lid was not a permanent fixture. It had been artificially propped up for years by patterns of precipitation and wind. And eventually, a combination of factors, changing winds, shifts in ocean circulation, and rising heat content in that deep layer, grew powerful enough to break through it. Once the lid failed, the system did not degrade gradually. It collapsed rapidly, dragging that long-buried heat up to the surface all at once, and sea ice that had spent a decade growing suddenly had nowhere left to hide. Researchers now describe the earlier growth phase not as a sign of stability, but as a period when the ocean was quietly storing up trouble, and the collapse that followed was that trouble being released. That is the backdrop against which 2026's numbers need to be read. When Antarctic sea ice hit its yearly minimum in late February of 2026, settling at around 2.6 million square kilometers, it registered as only the 16th lowest minimum in 48 years of satellite records, a return to something resembling normal after several years of extremes. Researchers monitoring the ice noted that for most of the year leading up to that point, the ice had actually been tracking well below its historical daily average, consistent with continuation of the post-2016 decline. It was only in January and February, in the final stretch before the summer minimum, that a shift in wind patterns pushed ice outward in the Weddell Sea specifically, slowing the seasonal retreat and pulling the final number back up towards something close to average. The scientists who tracked this data were careful, almost insistent, about how this result should be interpreted. They stressed that the improvement was real and worth noting since it sat meaningfully above the extreme low of 2023 by a margin of roughly 700,000 square kilometers. But they were equally clear that this should not be read as evidence that the underlying trend has reversed. One researcher pointed out that given how wildly Antarctic sea ice extent has swung from year to year across the full satellite record, a return to less extreme conditions after a period of anomaly was not, in itself, a shocking outcome. In other words, 2026's near average minimum is best understood not as recovery, but as noise, a single year where southerly winds happen to counteract the underlying decline, sitting on top of a system that a separate body of research suggests has already crossed into a fundamentally different, more volatile state than it occupied a decade ago. This is worth sitting with for a moment because it captures something important about how climate systems actually behave versus how they get described in casual conversation. We tend to want a single clean number, ice extent went up, ice extent went down, and to read that number as the whole story. But what happened in Antarctica between 2012 and 2026 is a lesson in how a system can look stable while quietly loading itself with instability, then flip into a new regime abruptly, and then produce individual years that look deceptively reassuring, even while sitting on top of a structurally altered ocean. The surface number, the one that makes headlines, is often the least informative part of the story. The real story lives in the layers underneath, in stratification and heat content and wind patterns that most people never see mentioned in a news chart. It is also worth pausing on how counterintuitive this makes life for the scientists whose job is to explain all of this to the public. Imagine trying to write a single accurate summary that captures both halves of this year at once. Lean too hard on the Arctic numbers alone, and you risk implying that every polar region on Earth is collapsing at the same accelerating pace, which overstates what actually happened in the South this particular year. Lean too hard on the Antarctic near recovery alone, and you risk the opposite distortion, suggesting that fears about Antarctic ice loss were overblown, when the very scientists who generated that data are on record warning against exactly that reading. This is precisely the kind of moment where nuance tends to get flattened, where a complicated, regionally divergent, mechanistically rich story gets compressed into whichever half happens to fit a listener's existing assumptions. The responsible reading requires holding both facts at once, that the Arctic is undergoing rapid, well-understood, accelerating decline, and that the Antarctic is behaving in a way so volatile that even a near-average year has to be read as a single data point sitting on top of a system already flagged as structurally altered, rather than as proof that the danger has passed. There is a further layer to the Antarctic story that pushes this analysis even deeper, because it is not just about sea ice floating on the ocean's surface. It is about the vastly larger ice sheets sitting on the continent itself, the ice that, if it entered the ocean, would raise global sea levels by meters rather than millimeters. A study published in Nature earlier this year, led by researchers associated with an Antarctic Environmental Research Initiative, offers what sounds at first like good news, then quickly complicates itself. The researchers found that scientists can likely forecast Antarctic ice sheet loss with reasonable reliability for the next 30 to 50 years, giving governments and coastal planners a genuine head start in preparing for the sea level rise that Antarctica alone could contribute. That's the encouraging half. The second half of the finding is the one that deserves more attention. Beyond that 30 to 50-year window, the researchers found that unstable ice retreat could accelerate dramatically, and once that happens, the system becomes far harder to predict with any confidence. In other words, we may currently be living through the most forecastable window Antarctica will ever offer us, a finite runway during which the physics remain relatively well behaved, before the system potentially crosses into a regime where ice loss compounds on itself in ways current models struggle to capture. Adding weight to that warning, separate research published this year has identified a previously underappreciated feature hiding beneath Antarctica's floating ice shelves, long channels carved directly into the underside of the ice by ocean water. These channels appear capable of accelerating ice shelf melt and structural weakening far faster than earlier models accounted for, essentially acting as highways that let warm water eat away at the ice from below in concentrated pathways rather than through even gradual thinning. And this isn't a purely theoretical concern. Satellite observations released in the past year documented the fastest glacier retreat ever recorded in Antarctica, when a section of the Hectoria Glacier suddenly broke apart and retreated 8 kilometers in a shockingly short window. Researchers attributed the speed of that collapse to the glacier sitting on a flat ice plain positioned below sea level, a geometry that, once destabilized, allowed enormous slabs of ice to break away almost all at once rather than eroding gradually over years. It stands as the fastest instance of modern ice retreat ever documented on the continent, and it illustrates exactly the kind of abrupt, self-accelerating behavior that researchers are worried becomes more common once Antarctica moves past that 30 to 50-year predictable window. Step back now and look at both poles side by side, because the contrast is the real story here, and it is more interesting than either pole's individual headline. The Arctic, in 2026, behaved almost exactly the way a simple, linear warming model would predict, just with numbers reaching new extremes. Record low winter maximum, record low ice volume, thinning ice, an ever-shrinking pocket of resilient multi-year ice retreating into its last strongholds near Greenland and the Canadian islands. It is decline, essentially on schedule, just accelerating. Antarctica, meanwhile, spent a decade breaking that same model in the opposite direction by growing, then broke it again by collapsing faster than expected. And then, in the very same year the Arctic was setting new record lows, produced a result that looked on paper like relative stability. Two poles, one steadily worsening in a straight line, the other lurching between extremes in ways that have repeatedly caught even specialists off guard. If you were designing a single global narrative meant to make climate change intuitive and easy to summarize in one sentence, this year's data at the poles would actively resist you. And that resistance is exactly why it matters. Public understanding of climate change has, for good reason, often leaned on simplicity, because complexity is harder to communicate and easier to dismiss. But nature does not owe us simplicity. And the growing body of research coming out of both polar regions this year is a reminder that the real system is layered, regional, and full of feedback loops that can either dampen or dramatically amplify a warming signal depending on conditions we are only now starting to fully map. There's an even deeper thread running underneath all of this, one that stretches back not years or decades, but millions of years, and it reframes the entire conversation about what actually drives Earth's climate at the poles. Scientists analyzing ancient air bubbles trapped inside deep Antarctic ice cores, tiny pockets that have been sealed away for up to 3 million years, recently uncovered something that genuinely surprised the researchers involved. They found that across that enormous span of time, the planet cooled substantially, particularly in the oceans, but the concentration of key greenhouse gases like carbon dioxide and methane barely budged during that cooling. That is a strange, almost paradoxical result if you assume greenhouse gas levels are the only lever controlling global temperature. If the planet cooled dramatically while greenhouse gases stayed relatively flat, something else had to be doing an enormous amount of the work. The researchers point to a combination of forces, including the growth and behavior of ice sheets themselves, shifts in deep ocean circulation, and changes in the planet's overall reflectivity, its albedo, as major drivers, operating somewhat independently of the greenhouse gas concentration story we usually center in climate conversations. This finding does not undercut the well-established link between greenhouse gases and modern warming. That link remains one of the most rigorously tested relationships in all of climate science. What it does is add nuance to how we should think about the polar ice system specifically, because it suggests those systems have their own internal dynamics, their own tipping points and feedback loops involving ice sheet geometry, ocean layering, and reflectivity that can operate on top of, and sometimes somewhat independently from, the greenhouse gas signal. It's a piece of the puzzle that helps explain why Antarctica in particular has proven so resistant to simple modeling. The continent's ice behavior is not simply a thermometer reading off atmospheric carbon dioxide levels. It's the product of an intricate, multi-layered system where ocean stratification, wind-driven currents, ice sheet elevation, and reflectivity all interact, sometimes reinforcing a warming trend and sometimes, for a decade at a time, appearing to resist it entirely. There's a companion discovery from earlier this year that pushes this even further back in time and adds an almost geological plot twist to the whole story. Researchers studying why East Antarctica became encased in ice millions of years before its northern counterpart found that the answer wasn't primarily about temperature or atmospheric composition at all, at least not directly. It was about elevation. Using detailed simulations, the team traced how the breakup of ancient supercontinents triggered slow-moving waves of material deep within the Earth's mantle, waves capable of causing land to rise dramatically over millions of years, in some cases even triggering volcanic activity far from any tectonic plate boundary. Their models showed that by roughly 45 million years ago, large portions of the East Antarctic landmass had been lifted by these mantle waves to an elevation of around 2 kilometers, right around the critical threshold needed for mountain glaciers to begin forming and, crucially, to persist and expand rather than melt back each summer. Once that threshold was crossed, individual mountain glaciers merged and grew into what eventually became the East Antarctic ice sheet, one of the largest single masses of ice on the planet. It's a genuinely striking reframing that one of Earth's most consequential ice sheets, the one holding back the largest potential contribution to future sea level rise, owes its very existence not just to cold temperatures, but to a slow-motion geological uplift process operating on a timescale of tens of millions of years. Antarctica's ice story, in other words, is layered across radically different timescales all at once, from mantle waves acting over tens of millions of years, to ocean stratification collapsing over the span of a single decade, to wind patterns nudging sea ice extent within the span of a single winter. If all of this sounds abstract, it might help to end where actual human beings are getting into the water to see these changes up close. Earlier this year, a group of scientific divers trained in a remote part of Finland, learning to descend through holes cut into thick lake ice in conditions where surface temperatures plunged to roughly minus 40 degrees, a specialized skill set being developed specifically to prepare researchers for work in genuine Arctic and Antarctic waters. Their broader mission reflects exactly the stakes described throughout this data. The Arctic is warming roughly 4 times faster than the global average, a disparity that ripples outward into weather patterns across the entire planet and is already visibly affecting wildlife, including polar bear populations that depend on stable sea ice as a hunting platform and are growing smaller, weaker, and hungrier as that platform shrinks and grows less reliable. In Antarctica, the melting of land-based ice sheets threatens to reshape coastlines globally through sea level rise, while also disrupting ocean ecosystems that have existed largely undisturbed for thousands of years. These divers are training to document what lives on the seafloor beneath both polar ice caps, cataloging plant and animal life that has adapted to near total darkness and extreme cold. Precisely because researchers recognize that these ecosystems are changing in real time and that nobody has a complete picture yet of what is being lost or altered, or in some cases just beginning to shift, while the ice above them behaves in ways their own models did not fully anticipate. It's worth also connecting all of this back to consequences that reach far beyond the poles themselves, because ice at the ends of the Earth does not stay contained to the ends of the Earth. Arctic sea ice loss has been linked by multiple lines of research to changes in the behavior of the jet stream, the fast-moving river of air that steers weather systems across North America, Europe, and Asia. A weaker temperature contrast between the rapidly warming Arctic and the mid-latitudes appears capable of making that jet stream wobblier and more prone to getting stuck, which some researchers connect to the kind of prolonged heat waves, extended cold snaps, and stalled storm systems that have become increasingly familiar in recent years. Meanwhile, the fate of Antarctica's land-based ice sheets carries a different but equally consequential downstream effect. Because unlike sea ice, which is already floating and does not raise sea levels when it melts, the ice sitting on top of the Antarctic continent represents one of the largest reservoirs of fresh water on the planet, and its loss translates directly into rising coastlines everywhere, not just near Antarctica itself. The Intergovernmental Panel on Climate Change has noted that under high emission scenarios, global sea levels could climb by more than 2 meters by the year 2100 if large sections of the Antarctic ice sheet become unstable, a scenario that would redraw coastlines and displace populations across virtually every continent, regardless of how far those communities sit from the Southern Ocean. That is precisely why the distinction between the predictable 30 to 50-year window researchers described in the murkier, more volatile period that could follow matters so much. It is not an academic distinction confined to specialist journals. It is the difference between planners around the world having decades of lead time to adapt coastal infrastructure or being caught by a system that stops behaving predictably right at the moment the stakes are highest. So where does all of this leave us? Not with a single tidy conclusion, and that itself is the honest takeaway. The Arctic is losing ice in a way that is largely predictable, accelerating and consistent with decades of warnings, but even there, regional surprises like the unusual Bering Sea ice buildup show that local weather and currents can produce outcomes that run counter to the broader trend for months at a time. Antarctica is behaving in a way that has repeatedly defied expectations for over a decade, first by growing when models said it should shrink, then by collapsing faster and more dramatically than anticipated, and now by producing a year that looks superficially reassuring while sitting on top of an ocean system that researchers believe has fundamentally changed its structure. Underneath both stories sits an even deeper set of findings suggesting that ice sheet geometry, ocean layering, continental uplift occurring over tens of millions of years, and shifts in planetary reflectivity all play roles in polar climate that operate somewhat independently of, and sometimes in tension with, the straightforward greenhouse gas warming narrative most people carry around in their heads. None of this is a reason for complacency, and it would be a mistake to read the Antarctic's near-average 2026 minimum as a sign that the danger has passed, because the scientists closest to that data have explicitly warned against that interpretation. But it is a genuine invitation to trade a simple story for a more accurate, more interesting, and ultimately more useful one. The poles are not two thermometers registering the same number in different locations. They are two distinct, deeply complex systems, each with their own internal feedback loops, their own thresholds, their own capacity to surprise the people who have spent entire careers studying them. What happened at both ends of the planet this year is a reminder that we are watching something genuinely unprecedented unfold in real time, not in some distant future scenario sketched out in a model, but right now, in data collected this winter and this spring by satellites and research stations and divers cutting holes through Arctic lake ice to prepare for work at the actual poles. The ice at the top of the world and the ice at the bottom of the world are telling two different stories this year, and understanding why those stories diverge, rather than forcing them into one convenient narrative, is exactly the kind of clear-eyed thinking this moment in Earth's history actually demands. There's also something worth noting about the sheer speed at which our ability to observe all of this has improved, because none of what you've just heard would have been knowable even a generation ago. Continuous satellite monitoring of both polar regions only stretches back to the late 1970s, which means scientists are essentially still assembling the first truly complete baseline of how these systems behave across multiple decades. Multiple El Nino and La Nina cycles, multiple shifts in ocean circulation. Every additional year of data doesn't just add a new point to a graph, it sharpens the entire picture, revealing patterns that were invisible with a shorter record and forcing revisions to models that looked solid a decade earlier. The compound Southern Ocean distratification mechanism identified this year, the buried channels, accelerating ice shelf melt from below, the mantle wave process explaining East Antarctica's ancient glaciation, none of these were widely understood even 5 years ago. That pace of discovery cuts in two directions at once. It means our understanding of what's coming keeps improving, giving planners better tools than they had before.